Okay, so today we're really going deep. We're talking about mathematical truth.
That's right.
And this might sound really abstract, but it gets to like the core of how we think about truth itself.
Absolutely. Yeah.
And specifically, we're looking at set theory,
Right.
which, you would think would be pretty straightforward, right? Like sets, things in sets.
It seems like it should be.
It seems like it should be, but as it turns out, it's anything but. And specifically, we're going to be talking about the quest for these new axioms. Axioms are kind of like the fundamental rules of the game in mathematics.
Yeah. The ground rules.
Yeah, and so we have this standard system called ZFC.
Right.
It's like the rule book that a lot of mathematicians use, but as we're going to find out, it doesn't answer everything.
Leave some pretty big questions hanging.
Yeah, and that's kind of the exciting part, for me at least.
Oh, absolutely.
Yeah.
It's where things get really interesting, especially for folks coming at this from a philosophy background.
Right, exactly.
We often think of mathematics as this perfect example of objective truth, like 2 + 2 = 4 no matter what.
Right.
But then we hit these limits in set theory, and it makes you wonder what truth even means in this context.
Yeah.
So this deep dive that we're doing today is all about how mathematicians and philosophers are wrestling with these boundaries of set theory. What happens when even our most basic assumptions about sets lead to unanswerable questions.
Exactly. And it all kind of started back in the 60s, right? Like mathematicians discovered these things called independence results.
Ah, yes. The 60s. A turbulent time for foundations.
Yeah. And so these independence results showed that there were these crucial mathematical statements that you couldn't prove or disprove using ZFC.
Right. So it's like the rule book of ZFC is incomplete. It has these gaps.
Yeah. It's like having a board game, but some questions about the game, like what's the best first move? The rule book just doesn't cover it.
Yeah. Perfect analogy.
Yeah.
Yeah. And it really throws a wrench into this idea of mathematics as this perfectly objective system, right? Where every question has a clear answer.
Yeah. So it makes you wonder, right? Like if there's more to mathematical truth than what we can squeeze out of ZFC.
Absolutely. And that's where this big philosophical divide comes in.
Yeah.
So on one hand, you've got the pluralist. They're like, well, maybe there isn't one single objective truth in mathematics, at least at this foundational level.
So it's like different universes of math almost.
Kinda, yeah. Different axioms, even if they contradict each other, could all be seen as creating valid mathematical universes.
So it's almost like a multiverse situation in math, too.
In a way, yeah. There's no single correct path.
Oh, that's really interesting.
And then on the other side, you've got the non-pluralists. They're not throwing in the towel on objective truth. They're saying, no, ZFC is just not the whole picture.
Oh,
We just haven't found the right axioms yet.
So it's like the quest for the holy grail of axioms.
Yeah. It's this drive to discover deeper reasons for why certain axioms should be adopted. Reasons that go beyond just the standard proof techniques in math.
It's like at a deeper level of intuition or something.
Sort of, yeah.
Okay.
And that's the side we're going to be exploring more today.
Okay. So we're going full-on non-pluralist today.
We're going to try to get into the heads of these mathematicians who are searching for these new axioms and the arguments they use to justify them.
Okay.
And it can get pretty heady. Like, we're going to be talking about some advanced concepts that blur the lines between math and philosophy. Like, what does it even mean to justify something in math? And what about this idea of mathematical realism? Is there this reality of math that exists independent of us? Or is it all just a human construction? Big questions.
Yeah, big brain-melting questions.
Exactly. And a key arena where these questions are being worked out is in this area called classical descriptive set theory.
Right. And descriptive set theory, it's all about studying these definable sets of real numbers. But it gets deeper than that, right?
Oh, yeah. It's like a microcosm of the whole foundational debate.
Okay.
And it turns out there are statements in descriptive set theory, specifically in this thing called second-order arithmetic. That's like regular arithmetic, but souped up to talk about sets of numbers. And these statements, you can't prove or disprove them from ZFC.
So even at this level, which feels pretty basic, we're already running into those independence results.
Precisely.
Okay, so before we even get to those new axioms, we need to understand how mathematicians even compare different systems of axioms, right? How do we know if one system is stronger than another?
Right. It's like, how do we compare different rule books in terms of how much they let us prove?
Right.
And the key idea here is this concept of interpretability. So imagine you have two of these mathematical rule books. Let's call them T1 and T2. And if you can translate everything you can say in T1 into T2, and all the proofs in T1 become proofs in T2 after this translation, then we say T1 is interpretable in T2.
So it's like T2 can do everything T1 can do and maybe more.
Exactly. It's like T2 is a more powerful language. And based on this idea, we can create a hierarchy of mathematical theories, kind of like a ladder, where each rung represents a stronger system.
So we're ranking these systems by their power level.
Exactly. And if two theories can interpret each other, we say they're in the same interpretability degree. They're basically the same strength.
Okay, that makes sense.
Now, there's this really handy way to characterize this idea of interpretability, at least for most theories that mathematicians actually use. These theories tend to be well-behaved. They can talk about basic arithmetic.
Right, the normal stuff.
Yeah. And for these theories, it turns out one theory being interpretable in another is the same as saying that all the complex statements of a certain type provable in the first theory are also provable in the second theory.
Oh, interesting. So it's like a shortcut to compare them.
Exactly. This is the famous Ori-Hajek characterization. It simplifies things a lot.
And I guess this is where things start to get kind of mind-blowing, right? Like this interpretability stuff combined with these deep results about the limits of proof tells us some really counterintuitive things.
Absolutely. For example, you know how we talked about adding a statement to a theory to make it stronger?
Right.
Well, if you take basic arithmetic and add the statement, arithmetic is consistent, meaning it doesn't have contradictions, that actually bumps the system up a level.
Okay. So saying it's consistent makes it stronger.
Weird, right?
Yeah.
But if you add this statement, arithmetic is inconsistent, you don't actually change the strength of the system.
Wait, what? So saying it's inconsistent doesn't make it weaker?
No, not in terms of interpretability.
That's really strange.
Yeah, it's a quirk of the logic of these systems. It highlights how sensitive they are.
Okay, so I can already tell we're getting into the weeds here. But what about this whole hierarchy of theories? Does it go on forever, or is there like a top level?
Well, the overall picture, if you consider all possible theories, gets messy. You have all these weird intermediate theories that can't even be compared to each other.
So it's like a tangled jungle of theories?
Yeah. But the amazing thing is when you zoom in on the natural theories, the ones mathematicians actually use, there seems to be a lot more order.
Okay.
It looks like a well-ordering, so no infinite descending chains. And any two of these natural theories, you can compare them in terms of strength.
So it's almost like there's this main path through the jungle that these natural theories follow.
That's a good way to put it. And along this path, there's this canonical sequence of theories. You start with these really weak systems, and then you keep adding these closure principles that let you talk about more complex things.
So it's like climbing a ladder. Each rung is a stronger theory.
Exactly. And these closure principles, they give us the ability to talk about things like fast-growing functions, infinite sets, and eventually these incredibly huge infinite numbers called large cardinals.
So we're starting from like the simplest math and building up to these crazy infinities.
Exactly. And this hierarchy is really crucial when we're thinking about this debate between pluralism and non-pluralism, because some of the rungs on this ladder correspond to these philosophical viewpoints on math.
Okay.
For example, you have strict finitism, which is like we can only talk about finite things, and that corresponds to these really weak theories down at the bottom of the hierarchy. Then you have finitism, then predicativism, which draws a line about what kinds of definitions are okay. All these are philosophical positions that are trying to figure out where objectivity ends and where things become more open to interpretation.
So it's like each rung on the ladder might be a place where someone draws a line and says, math up to this point is objective, but beyond this, who knows?
Exactly. The hierarchy helps visualize these philosophical boundaries.
And I guess it's worth mentioning we also have to be careful about what kind of independence result we're talking about.
Right. It's not all the same.
Yeah, so there's vertical independence. This is when adding a statement makes a theory strictly stronger. Like we talked about with adding arithmetic is consistent to basic arithmetic, or adding a large cardinal axiom to ZFC. Those are vertical jumps.
Right. You're moving up the ladder to a new interpretability degree.
Exactly. But then you have horizontal independence. This is where a statement is independent, meaning you can't prove or disprove it, but adding it or its negation doesn't actually change the strength of the theory.
Right, you're staying on the same rung of the ladder, but exploring different branches.
Right, and these are often called ORI sentences, like the continuum hypothesis, that famous one about the size of the set of real numbers, or other statements about sets of reals.
Exactly. And the horizontal independence results, they're really at the heart of this pluralism debate.
So we've got these different theories, different kinds of independence, but how do we actually make this question of pluralism more precise, especially for someone who's coming from a philosophy background?
Well, one way to sharpen the question is to stick to a common language, right? And set theory, with its focus on sets, is pretty much the universal language of math. Almost anything can be formulated in set theory.
So if we want to have a clear debate, it's like saying everyone has to use the same dictionary.
Exactly.
Okay.
So pluralism in this context is basically asking,
Mm-hmm.
as we climb this ladder of stronger set theories, is there one correct path? Or are there multiple equally valid paths?
Okay. So that's a way to frame the question more precisely. But even then, it seems like a really tough question to answer, right?
Absolutely. It breaks down into two main challenges. One is the problem of consistency. How far can we extend this ladder of theories without running into contradictions?
Okay, that makes sense. We don't want our math to implode.
Right. And the second challenge is the problem of selection. If we're on one rung of the ladder and there are multiple ways to go up, what criteria do we use to choose?
So it's not just about avoiding contradictions, it's about figuring out which extensions are the right ones.
Exactly. And even within our standard system, ZFC, we have this problem. Like with the continuum hypothesis, there's no consensus on whether it's true or false.
Right. So even before we add new axioms, we're already stuck on some big questions.
Yeah. And today we're really focusing on that selection problem.
Yeah.
We're assuming ZFC is okay for now, but we're trying to see if there are good reasons to prefer some ways of extending it over others, especially when we're dealing with statements about sets of numbers and beyond.
Okay, that makes sense. And just to be thorough, I guess it's worth mentioning the most extreme kind of pluralism, right?
Radical pluralism?
Yeah. What's that all about?
That's the view that all consistent mathematical theories are equally valid. So basically, anything goes as long as it doesn't contradict itself.
Okay, so it's like complete freedom of choice in math.
Sorta, but most philosophers, even those sympathetic to pluralism, find this view a bit too radical.
Why is that?
Well, it runs into some logical and philosophical problems. It's hard to make sense of mathematical practice if every consistent theory is equally valid. Mathematicians clearly prefer some theories over others, and for good reasons.
Right. It would be like saying every possible board game, no matter how nonsensical, is equally good.
Yeah, something like that.
And I guess the limitative philosophies of math, like predicativism, are examples of these more nuanced pluralist views.
Exactly. They're kind of a hybrid.
Okay. So, like, a predicativist might accept basic arithmetic as objectively true, but get all pluralist about some parts of set theory.
That's the general idea.
So they're drawing the line somewhere on that ladder of theories we were talking about.
Right. And that line's based on philosophical principles about what kinds of definitions are legitimate and what kinds of sets are too abstract to be considered objective.
Okay, that makes sense. So to be clear, the non-pluralist perspective we're focusing on today, they're not throwing out ZFC. They're just trying to find strong reasons to choose certain extensions of it.
That's right. It's a common starting point, a kind of working hypothesis. We accept ZFC as a reasonable foundation and then try to build up from there.
Okay, so we've talked about this hierarchy of theories, different kinds of independence results. But I guess now we should get down to the building blocks, right?
The axioms themselves.
Yeah, like where do they even come from? How are they justified?
Mm-hmm.
If we can't just prove them from something else, what makes us believe they're true?
Big questions. And that's really where the philosophy of math comes in, right?
Totally.
So traditionally, we justify a mathematical statement by showing it follows logically from accepted axioms.
Right. But that just kicks the can down the road, doesn't it?
Exactly. Because then what justifies the axioms themselves? Why should we accept those starting points?
Yeah. And, the radical pluralist would just say, axioms are just postulates. We choose them because they lead to interesting math.
Yeah. But that doesn't really sit well with most mathematicians and philosophers.
Right. It feels like axioms should be more than just convenient assumptions. Like, there should be some reason to believe they're actually true about something.
Exactly. And historically, a lot of mathematicians appealed to this idea of axioms being self-evident truths.
Like, so obvious you can't doubt them.
Yeah, that was the idea. For example, some of the basic axioms of arithmetic, They seem pretty self-evident, right? Like,
Yeah.
if you have 2 apples and you add 2 more apples, you have 4 apples. That's just how numbers work.
Right. It's hard to argue with that. But I guess the problem is not all axioms have that kind of immediate apple counting obviousness.
Yeah, especially when you get to more abstract realms like set theory.
Right. Like, what does it even mean for an axiom about infinite sets to be self-evident?
Exactly. It becomes very murky. And if we only stuck to axioms that everyone agreed were absolutely self-evident, our math would be pretty limited.
So we need a more nuanced approach, right? Something beyond just this idea of self-evidence.
Absolutely. And one idea that's been influential is this notion of relative evidentness.
So instead of saying an axiom is self-evident in some absolute sense, we're comparing axioms to each other.
Exactly. Even if we don't think an axiom is undeniable, we might still have a strong intuition that it's more fundamental, more basic, or just more plausible than another axiom.
Okay, I'm following. So it's like a ranking of axioms based on how evident they seem.
Exactly. And a fascinating way to see this in action is through these equivalences that mathematicians have discovered. Sometimes you have two statements that seem completely different from different areas of math, but it turns out they're logically equivalent.
Meaning, if you prove one, you automatically prove the other, and vice versa.
Exactly.
And that can tell us something about which statement is more fundamental.
Exactly. So, for example, you have this result called the finite Ramsey theorem. It's this pretty complex statement in combinatorics about how when you color the edges of a complete graph, you're guaranteed to find certain monochromatic subgraphs.
Okay, I'm already lost. But I trust you, it's a complex statement.
Yeah.
Yeah.
It takes a bit to explain. But the point is, it's logically equivalent to the statement that the function of iterated exponentiation is always well-defined.
Okay, and what's iterated exponentiation? Sorry, I'm a little rusty on my math jargon.
No worries. It's like repeated exponentiation. So like 2 to the power of 2 to the power of 2 and so on, a certain number of times.
Okay, so basically you're saying there's this complex theorem about coloring graphs that's equivalent to saying that this repeated exponentiation thing always makes sense.
Exactly.
And which one seems more evident, more basic?
I think most people, even if they're not mathematicians, would say that repeated exponentiation making sense is a lot more basic than this intricate Ramsey theorem.
Right. It feels like the Ramsey theorem should be a consequence of something more fundamental, not the other way around.
That's the intuition. And you see this kind of thing pop up all over math.
Really?
Yeah. Like the Hilbert basis theorem, a key result in algebra, is equivalent to saying that the set of natural numbers with their usual ordering is well ordered up to a certain point. Goodstein's theorem and the Hydra theorem, these two tricky results in number theory, they're equivalent to saying that basic arithmetic is consistent for certain statements.
So these complicated theorems are really just elaborate ways of saying something that seems pretty straightforward.
That's one way to look at it.
Mm-hmm.
And then you have Kruskal's tree theorem, this really deep result in combinatorics, which turns out to be equivalent to saying that a certain very large ordinal number is well ordered.
Wow, so these equivalences are like hidden connections between different areas of math.
Exactly. And they give us a clue about this idea of an evidentness order.
Okay, let's break that down. What's an evidentness order?
It's a way of organizing mathematical statements within a given level of complexity based on this more evident than relation.
So it's like a ranking system, but instead of ranking by difficulty, we're ranking by how fundamental they seem.
Exactly. And it's really important to stress that more evident doesn't mean self-evident in some absolute sense. It's more about a relative judgment of plausibility, of which statement seems more basic.
Okay, so it's not like a binary thing where a statement is either self-evident or not. It's more like a spectrum.
Exactly. It's an epistemic order, meaning it's about how we come to know and accept these statements, not just about their objective complexity.
Right. And you're not claiming we can compare every pair of statements this way, right?
Of course not.
Yeah.
There are definitely cases where it's not clear which statement is more evident. But in many important cases, there seems to be a pretty clear and widely shared intuition.
Okay, that makes sense. But, a philosopher might push back and say, hold on, maybe this whole evidentness order is just a product of our training. It's just how we've been taught to think about math.
That's a fair point. But there are examples where even someone without specialized training can see the difference in evidentness.
Like what?
Well, consider the Hydra game. It's this game where you're chopping off heads of a Hydra, and each time you chop one off, it grows new heads according to certain rules. And there's this theorem about how no matter what strategy you use, you'll eventually defeat the Hydra.
Okay, I vaguely remember hearing about this.
The thing is, this Hydra theorem, is equivalent to saying that a certain ordinal number, called epsilon naught, is well ordered.
And I'm guessing the well-ordering thing seems more evident.
Even without knowing the details of what epsilon naught is, most people would find it more plausible that some kind of ordering of numbers is well behaved than this weird Hydra game where heads keep sprouting.
Yeah, that makes sense. The Hydra thing feels like it should be a consequence of some more basic principle about order.
Exactly. And that intuition, that sense of which statement is more fundamental, is what we're trying to capture with this evidentness order.
Okay, so when we're searching for new axioms, we want ones that are low down in this evidentness order.
Ideally, yeah. We want axioms that seem as basic as possible, the most fundamental assumptions we can get away with.
So it's like building our mathematical house on the most solid foundation possible.
Exactly. But we also want our axioms to be secure. We need good reasons to believe they're true, not just that they seem evident.
Right, and I'm guessing that as we climb that ladder of theories, the axioms that seem evident at each level might get more and more complex, less and less obvious.
That's exactly the challenge.
So is finding these minimal evident axioms the best we can do? Or are there other ways to justify new axioms?
That's the million-dollar question. And it leads us to this really important distinction made by Kurt Gödel, the famous logician. He talked about intrinsic and extrinsic justifications for axioms.
Okay, tell me more.
So intrinsic justification, according to Gödel, comes from unfolding the very concepts we're working with.
So it's like digging into the meaning of the concepts themselves.
Exactly. And for Gödel, the concept of set has this built-in idea of iteration. You can have sets of sets of sets of sets and so on going on forever.
Okay.
And this iterative nature of sets, it suggests that there should be these really huge infinite sets, these large cardinals.
So the very idea of a set is pushing us towards these incredibly big infinities.
Exactly. And Gödel thought that axioms about large cardinals, they weren't just arbitrary assumptions. They were making explicit what was already implicit in the concept of set.
Okay, so that's intrinsic justification. What about extrinsic justification?
That's a bit different. It's about looking at the consequences of an axiom, its fruitfulness.
So it's not about the axiom itself, but about what it can do.
Exactly. If an axiom leads to a bunch of interesting results, helps us solve problems, brings order to a whole area of math, then that's evidence in its favor.
So it's like saying, this axiom might not be immediately obvious, but look at all the cool stuff it lets us do.
Yeah, that's the basic idea. And Gödel even suggested that if an axiom is super successful, we might have to accept it as true, even if we don't fully grasp its intrinsic necessity.
Okay, that's interesting. So it's like we're judging an axiom by its fruits.
Exactly. Now, think about the principle of mathematical induction. This is the idea that if a property holds for 0, and if whenever it holds for a number, it also holds for the next number, then it holds for all natural numbers.
Right. That seems pretty fundamental.
Yeah, and it feels intrinsically justified by our understanding of the natural numbers. That's like built into the very concept of how they're generated.
Okay.
Now, contrast that with a statement like, ZFC plus a gazillion wooden cardinals is consistent.
And wooden cardinals are.
Oh, they're in another type of large cardinal, even more mind-bogglingly huge than the ones we talked about before.
Okay, let's just say they're really, really big.
Yeah. But the point is, that statement about ZFC plus wooden cardinals, it doesn't feel intrinsically justified by our basic understanding of numbers or sets. It's not something you just see by reflecting on the concepts themselves.
Right. It's not apple counting obvious.
Exactly. Its justification comes from this whole web of theorems and connections within set theory.
So it's like a more indirect kind of justification.
Exactly. And this is where things get really interesting for the philosophy of math. Because some philosophers think that intrinsic justification, this unfolding of concepts, it's essentially the same as finding those minimal points in the evidentness order.
So the most intrinsically justified axioms are also the ones that seem the most basic, the most fundamental.
That's the idea. But if that's true, it might mean there are limits to what we can justify intrinsically. And that could push us towards pluralism for statements that go beyond those limits.
So, like, maybe we can intrinsically justify some basic axioms, but for the really powerful high-level stuff, we're left with a bunch of equally valid options.
That's one possibility. But extrinsic justification offers another way forward. It says we can build a case for an axiom by showing it leads to consequences that are themselves intrinsically plausible or that bring a lot of order to math.
So it's like bootstrapping our justification. We start with some axioms that seem evident, and then we use those to justify other axioms that might not be so evident on their own.
Exactly. And if we can show that our new axiom is the only way to get those desirable consequences, or that many other plausible statements independently imply our axiom, then the case for it becomes much stronger.
Okay, so it's like a web of interconnected evidence.
Exactly. And that brings us to this really exciting area where all these ideas are playing out. Classical descriptive set theory.
Okay, let's talk about descriptive set theory. It's all about studying these definable sets of real numbers.
That's the basic idea. And the real numbers, they're the continuous numbers, the ones that make up the number line.
Right. And definable sets, those are the ones we can describe in some precise way using logic and math, right?
Exactly. And historically, this area really took off in the early 20th century. Mathematicians like Borel, Baire, Lebesgue, they were all making huge strides in understanding these definable sets.
Okay, so it was a hot topic back then.
Definitely. Yeah. And they were particularly interested in the properties of these sets, like their size, their structure, how they behave under different operations.
Right, like trying to classify and categorize them.
Exactly. But after a few decades of amazing progress, things seemed to hit a wall around the 1930s.
Like they'd reached a dead end.
And we now understand why that happened. It was because of those independence results we talked about earlier. The questions they were trying to answer, they were unanswerable in ZFC.
So they were literally pushing up against the limits of their axiomatic system.
Exactly. And it's remarkable how far they got without realizing those limits were there.
It's like they were exploring a continent and suddenly ran into an ocean.
Yeah. And those independence results, they basically showed that if you wanted to make further progress in descriptive set theory, you needed new axioms.
Okay, so this is where the search for new axioms really gets going.
Precisely. And there were two main approaches that emerged. One was to add axioms about something called definable determinacy, and the other was to add large cardinal axioms.
Okay, and I'm guessing these are connected to those two kinds of justifications we talked about, intrinsic and extrinsic.
That's exactly right. But before we get to those, let's just lay out some of the basics of descriptive set theory. When we talk about real numbers here, logicians often use something called Baire space as a stand-in.
Okay, and Baire space is?
It's essentially the set of all infinitely long sequences of natural numbers.
Okay, so it's like a more abstract way of representing real numbers.
Exactly. It turns out to be mathematically equivalent for many purposes in this context, and it's often just more convenient to work with.
Okay, fair enough. So within this Baire space, we're interested in sets of these infinite sequences that are definable, meaning we can build them up from simpler sets using well-defined operations.
Exactly. And we can organize these definable sets into hierarchies based on how complex their definitions are. One of the most important is the Borel hierarchy.
Okay, let's hear about the Borel hierarchy.
So you start with the most basic open sets in Baire space. An open set is kind of like a region without its boundary.
Yeah.
And then you repeatedly take countable unions and countable intersections of these sets.
Countable meaning like you can count them with the natural numbers.
Exactly. And this process generates a whole layered structure of sets, denoted by sigma 0 alpha and pi 0 alpha, where alpha is an ordinal number, which is like an infinite counting number.
Okay, so we're building up more and more complex sets using these countable operations.
Precisely. And a key result is that this hierarchy is proper, meaning that at each level, you get new sets that weren't at the previous level.
So it's like a ladder of complexity.
Exactly. Then we have the projective hierarchy. This one starts with closed sets, which are like the complements of open sets, and then we add two more operations. Taking the complement of a set and taking the projection of a set.
Okay, and a projection is?
Imagine you have a set in a higher dimensional Baire space, so a space of longer sequences. Its projection is like its shadow in a lower dimensional space, a space of shorter sequences.
Okay, so it's like taking a 3D object and projecting its shadow onto a 2D plane.
That's a good analogy. And this iterative process of taking complements and projections also creates a hierarchy of sets, denoted by sigma 1n and pi 1n, where n is a natural number.
Okay. And I'm guessing these hierarchies are connected to that second-order arithmetic you mentioned earlier.
Exactly. They correspond to the complexity of defining these sets using the language of second-order arithmetic. So sigma 1n means you can define the set using all alternating quantifiers over sets of integers. starting with an existential quantifier.
Okay, and quantifiers are those things like for all and there exists, right?
Exactly. And the boldface notation means we're allowed to use real numbers as parameters in our definitions. It's a more powerful language.
Okay, so the boldface hierarchy is like the deluxe version.
Uh-huh. Yeah, something like that.
And we can even go beyond the projective hierarchy, right? To this L.